extending across space, but moving across time. But what's interesting here? Well, it makes something else jump out at you. Imagine this is a bus, and the bus is going up a street, and then it turns at the corner. So it's going a different direction. What happened to the bus? This happened. Rotation. Because you're going in a different direction. And so here I am going in this direction, but if I change the direction, such as this direction here, rotation has occurred, which means my spaceship begins to extend across the dimension of time, and less of it is extending across the dimension of space. That means that the faster I move across space, the more rotation occurs, thus the shorter my spaceship becomes, as far as spatial length goes. Now, the overall length stays the same, but that's extending across time as well, right? And of course, we can look across space, but we can't look across time, so you can't see the complete constant length of it. We're always confined to just the present time. So as a consequence of that, all we would be able to notice is the shrinking of the spatial length. Okay, so next, again, this constant motion determines the maximum speed at which you can move across space, and also the maximum speed at which you can move across time. Next, I'll take this spaceship and have it going in this direction, such that it'll be moving through time at half of the maximum possible speed at which you can move across time. Okay. Okay, so there's the one going in this direction. Again, we're moving through time here now at half of the maximum speed possible. That means we're going in this direction. And that'll determine also the speed at which you're moving across space. So the actual direction we're traveling is like this. And okay, so now I'll put the object in, the spaceship. Okay. So it looks like it's shrunk down to about half its previous length, but it'd be nice to come up with equations to calculate that. But anyway, so far what we have here, I'll call this the maximum speed at which you can move through time. I'll call that t. This is a variable here. Time slows down. How much is depending upon which direction you're going. So I'll call that t prime. This here I'll call length. It doesn't change, stays the same. L for length. This is your constant motion, so I'll call that c for constant. This here is the speed at which you're moving across space, and so we'll call that v for velocity, and so forth. Now, again, it'd be nice to come up with a formula to calculate how much this is contracted in length. Well, the first thing you notice is that what we have here available is a right-angled triangle. And that can be useful because I have length, or L, the same length as C. It's at a 90-degree angle. So what I can do is basically take this triangle out and move it over here, or create two identical triangles. That's going to be our first step in producing equations. Okay, so here we have a variable, the length, so we'll call that L prime. This side I'll call B. This side here I will simply call A. Now, what's the purpose of the triangles? Well, the idea is let's assume we have information available such as the speed at which you're moving across space, the velocity, and this constant motion. If you want to calculate what the new length is, you can possibly transfer information over from one triangle to the other. But to do so, you have to make sure they're of equal scale. But first, to start creating equations, we take advantage of the Pythagorean theorem. The square of the length of the hypotenuse of a right-angled triangle is equal to the sum of the squares of the remaining two sides. And so in this case here, with this triangle, we have c squared equals a squared plus v squared. And this one we have L squared equals L prime squared plus b squared. Now, like I've said, these two match in length. I've matched them in length. But not every object is going to be somehow related to that constant motion. In other words, we don't have just one length within the universe. So we could have a smaller triangle, so it's not a complete match. But that's easy to fix. What we'll do is just reduce both of these to a scale of 1, and that can be done by taking advantage of division. So we end up with a squared over c squared plus v squared over c squared equals 1. The next one we have L prime squared over L squared plus b squared over L squared equals 1. So now we've matched them on a 1-to-1 scale. Now, assuming we have the information of v and c available, we can therefore replace this with this and move on from there. So we have L prime squared over L squared plus v squared over c squared equals 1. Then we can start rearranging that. So we have L prime squared over L squared equals 1 minus v squared over c squared. Then you want to move this over. L prime squared equals L squared times this, 1 minus v squared over c squared. Then you want to get rid of the squares, so you take the square root of this instead. So you have L prime equals L times the square root of 1 minus v squared over c squared. So there you have the final equation to calculate how much your spaceship or whatever it is going to contract to, the new length. Okay, now it would also be nice to be able to calculate, based upon velocity and this constant motion, how much is time going to slow down depending upon those two factors. Well, that's easy to do. We'll use substitution again. You notice that t prime is equal to a. And the length of t is the same length as c. And so you can change this here to t prime squared over t squared. And then you already have your v and c within the equation. So you just do your usual rearranging and you end up with an equation delta t prime equals delta t times the square root of 1 minus v squared over c squared. Now by delta, I just mean a certain time period. For instance, T1, let's say, is 11 o'clock. T2 is 12 o'clock. So something started at 11, finished at 12. So the delta time period would be T2 minus T1. 12 o'clock minus 11 o'clock equals 1 hour. So it's just a certain time period. Anyway, we have two equations so far, simply by using geometry of the very basic scale and Pythagorean theorem. And how much simpler can you get? How much simpler could it be? Okay, so what we'll do now is move these equations up to the top so we have some more room to work with. Okay, so we have L prime equals L times the square root of 1 minus V squared over C squared. Then we have delta T prime equals delta T times the square root of 1 minus V squared over C squared. So there's our first two equations there. Now at this point you think, gee, are we onto something, right? Because you have no education in physics. So you do what I did. You borrow a physics book, or today I guess you'd look in the internet, and you check to see if these equations are found anywhere in the world of physics.